Okay, thank you. Thank you for the introduction. Yeah, so Honor, I actually saw him last week at UBC. So he works more on the architecture side, and we're trying to figure out how to use processing memory for applications. So it's a pretty crazy new technology, and hopefully I will provide some entertainment. Although I understand that it might be difficult for some of you to stay awake. So let's go straight into this. So storage, memory, and processing, we usually think of these parts of the system as separate. So we even have this labels that we assign to them, as in storage as persistent slow, and built as a, packaged as a hard disk drive or a SSD and made from flash or other magnetic media. And memory is volatile, fast, built from DRAM as SRAM. And processor is usually something that sits far away from memory and storage, and it's usually stalled, waiting for instructions or data to arrive from those. And we even have separate benchmarks and separate conferences dedicated to these. And one of the current trends, which is disaggregation, is indeed pulling these three parts of the system even further apart. But another trend is blending them together. So we have persistent memory from Intel Optane, which takes memory and makes it more like storage, and takes it storage and makes it more like memory. The product Optane has been discontinued, but persistent memory has not. It's been around for decades, and it'll show up. It'll come back in one shape or form, is what is believed. Then we have processing in storage, and lots of research is being done with open SSDs. And now we have processing in memory. The processing in memory has been around in research for decades, I would say, but now there are actual products. And the thesis of this talk today is that blending of these technologies can make disaggregation more practical. So we have these two opposing trends, and it seems that they're opposing, but they can actually help each other. So first, let's talk about disaggregated storage. I mean, it's not anything new. We've had this around for more than a decade, probably a couple of decades. So disaggregated storage means that you have nodes that don't have much storage attached, and then you have actual storage nodes, and they are attached to the network, and you access them via the network. And that was not so difficult to embrace, because as networks became faster, the network latency became comparable to that of a directly attached device, right? So we're talking, microseconds. If it's old spinning disks, then it's even milliseconds. And so networks are in that ballpark right now. Sometimes, depending on how much data we're trying to push between compute nodes and storage nodes, bandwidth could be constrained. So let's take that challenge, constrained bandwidth, and let's see how computing near storage or computing in storage can help us address this problem. And I'm going to give you one example. Again, it's not very new work, a couple of years ago, and you probably have seen these papers, or maybe not. But basically, the idea is that we run application logic inside the device. There have been a couple examples in the literature. So LightStore is a key value store implemented in SSD. My student currently is building the entire file system inside SSD. And one of probably more sophisticated ones is REC SSD. And so REC SSD has to do with machine learning and recommendation models. So, the ones that make, Netflix and Google sell you stuff, right? So they figure out what it is that you're supposed to want and like. So those models can get pretty large. the larger the model is, the more accurate it is likely to be. And some providers claim that they have models that are terabytes in size. And so if you have a large model and it's sitting somewhere on SSD, then pushing this data to CPU to perform an inference and then discarding this data, can really constrain our bandwidth and put pressure on our network. So one idea was, okay, let's do this computing on a model, the inference, basically, traverse the model representation and come up with a recommendation. Let's do it directly on the SSD. And if you're interested to learn about how that went, here's a reference for a paper. So we're not going to talk in detail about this work. What's more important is an example, is that so we have a storage device that now has memory and has processing inside of it, and leveraging those resources helped us address some of the challenges of disaggregation on a data center scale. So if we think about that, okay, DLRM, deep learning recommendation models, take a large number of cycles in many organizations, then we can build disaggregation more aggressively into servers that are using those cycles, because the device that is equipped to perform computing can address some of the challenges with disaggregation and can make it more practical. So it's, with storage, disaggregation is not so crazy. But with memory, it is less obvious. So disaggregated memory has been popular in the research community. But, in the industry, it's still considered one of those fringe technologies. And sometimes when I tell industry folks about disaggregated memory, they look at me and say, why? Why would you ever want to do that? So here's some motivating data. According to numbers from real data centers, the average memory utilization in servers is about 60%. So, you have a bunch of servers and you have RAM in each server, and, it's used to only about 60% on average. But the distribution is not uniform. If it were uniform, we could just give less memory to each server and we would save money. But it's not. So what usually happens is that some machines use almost all of their memory, or they even try to use more than they have, and lots of jobs are getting killed because of that, because we run out of physical memory and we don't enable swapping for performance reasons, or for accounting, or other reasons that are cloud specific. And so at the same time, other machines are underutilizing their memory. And so what we have is that some machines are not using all of their memory and others are using more than the machine has. And, looking at that picture, we're thinking, okay, wouldn't it be nice if the first machine could share the memory with the second? And this is exactly where the motivation for disaggregated memory comes from. So the idea is that we're going to place our memory nodes or blades onto the network and expose them as, one big elastic memory pool. And then compute nodes are just going to allocate memory from there as they need. And because it's a large elastic pool, it's easy to, get more memory when you need and then release it when you don't. Now, the challenge with this idea is that network latency is orders of magnitude higher than that of local memory. So we're talking about hundreds of nanoseconds for local memory and tens of microseconds for remote memory. And that is, even if we do everything right, we bypass the kernel overhead on the software stack, and was super efficient with our networking. We use RDMA and all the bells and whistles and the latest keywords. The best that I've seen in the literature is like tens of microseconds that we can do for remote memory access. And there are other challenges too. So if you have memory now spread across actually different machines, how do you manage it? How do you translate virtual to physical, and who keeps those translations? And how do you allocate memory across machines, and all of these issues? So the solution space to these challenges ranges from somehow addressing high latency issues with caching, classical computer science solutions. So we add some DRAM caches on CPU nodes, so you don't have just disaggregated memory, you also have some DRAM on your CPU node. But of course, caches work well when they're large enough, and if we put lots of DRAM on the CPU node, then that defies the purpose of the disaggregated memory, because we're back to the original problem that we began. Another way to solve high latency is fast networking. The actual hardware, RDMA, user level networking, and other new hardware that is being proposed by research in research. And then there are solutions to remote memory management. So now our memory nodes have not just memory, but also the CPUs that manage that memory, and that of course makes those memory nodes more expensive. We can use a separate metadata server. We could have in-network memory management and programmable switches that are a pain to program. So but there are solutions out there. So I'm going to propose a more radical solution, which comes in the shape of processing in memory. But first, let's talk about processing in memory. Like I said, it has been around for decades. And in general, it refers to a broad class of technologies, from changing how the memory fabric is implemented, so you actually have gates that can compute, to something simpler, where we have processors that are sitting very close to memory and are doing work directly on that memory. So it has been in research for more than a decade, but most of these ideas, they have not been built, let alone available as actual products. But recently, things have changed. So we have two commercially available solutions. So let me first quickly talk about the second one that I have here, which is Samsung Function Memory Architecture. I don't know if it's actually available commercially at the time of this writing or as a prototype. Its impact is quite limited. It's for HBM, so it's very expensive, high bandwidth memory that's limited in size. And the programmability is limited, so you can execute very short 32 instruction snippets. There's only a total of 9 instructions available. Programming is difficult, and it's function in memory, and it's for acceleration of specific functions that mostly targeted at machine learning. Now, the first one on the slide, it's a commercially available, meaning you can actually buy it or even access it for free if you're a researcher and if you have some friends and friends. So this is technology from Grenoble, and it's actually a DRAM DIMM that has processors inside, and it can perform computing. So let's look at it more closely. So it looks like a regular DRAM, and it can be used actually as a drop-in replacement for DDR4 DRAM. But the difference is that each chip is equipped with small processors, and it can be used in off-the-shelf servers. So, you buy a regular server for Intel, you buy these chips from UpMem, Then you do perform a little bit of magic with with BIOS upgrade, and voila, you have your computing and memory technology in your own lab. So what's inside this DIMM? So each 64 megabyte slice of DRAM has its own DRAM processing unit, which is a very simple general purpose in-order processor. If anybody's familiar with Sun Microsystems Niagara or ROG, it's so they had a stint with a simple multi-threaded processor about, I don't know, 20 years ago. So if somebody's familiar with that, it's very much like that. So it's there's no cache, only scratch pad memory, and it runs at a pretty low clock rate from 267 to 500 megahertz. The main challenge with upping the clock frequency is power. The board, so it attaches to the CPU board, and it just doesn't have enough power to increase the clock frequency. You can sort of hack it by attaching extra wires to the board and supplying it more power. But short of doing that, the systems that we have available to us today run at 350-ish megahertz. So the processing is quite limited, but it's a general purpose processor, and you can write code in C, and there is a compiler, and you can basically just run your C program and compile it to run on those. So the important part here, so I mean, why even care building this technology, is that so we have one processor per each 64 megabyte slice of RAM, and so each of the slices has a dedicated DMA engine. So a processor has a direct line to its 64 megabyte slice of RAM, and there isn't contention for bandwidth with other CPUs, which is what we will see in conventional DRAM. And there's lots of those. So for an 8 gigabyte DIMM, we have 128 DPUs. So there's lots of processing power. It's very parallel, but each DPU only sees its own local slice. It does not have direct access to slices of other DPUs. So if we want to share memory between DPUs, we're going to have to go through the CPU, and that's going to be our bottleneck. So the superpower of this architecture is that many DPUs working together can achieve a very high DRAM bandwidth. So here's a chart. We have throughput in gigabytes per second on the y-axis, and we have the amount of memory in gigabytes on the x-axis. What we're running here is a very simple workload where we read every single byte of memory. And what we see here is very interesting. So the flat curves, the red and the yellow one, are for DDR4 memory channels. So we have, one channel on the bottom here at about 19 gigabytes per second, and 4 channels at about 76 gigabytes per second. And that's it, right? So it's the memory bandwidth is limited by how many channels you have, and if you want to add more channels, it's not that easy. Only very high-end and expensive CPUs have lots of channels. So with GPUs, the bandwidth scales as we add more memory. Because we add more memory, we have more GPUs, and so we're able to, so more GPUs and more DMA engines. So we're able to access all of this bandwidth together in parallel because we're sitting inside this chip. Of course, this workload is embarrassingly parallel. Each CPU is working at its own 64 megabyte of RAM, and they're not talking to each other. This is like, the simplest workload that can showcase this technology. And of course, the question that we ask is, are there other realistic applications that can leverage this technology as much as possible? So here are a couple of examples where we were successful at getting good scaling on PIM. So this experiment shows you snappy compression implemented inside those PIM chips. The y-axis is the throughput relative to host CPU, so higher numbers are better. The x-axis, the bottom x-axis, is the file size. As we increase the file size, we spread it across more chips. And the top x-axis shows you the number of DPUs that we use. So we also have more DRAM processing units that are working in parallel in this technology. And you can see that basically we do get scaling as the data size increases, but your mileage may vary depending on what your compute to data transfer ratio. And we'll get to that a bit later. So this is a very very good example of when this processing and memory technology can really shine. So what we have here is hyperdimensional computing. So it's a similar chart where we have speed up on the y-axis, so higher numbers are better, DPUs across the top x-axis, and file size and also the memory size across the x-axis. And here, even though we're using tiny amount of data, we already see very good speed up relative to the CPU. So this showcases the best case for this processing memory technology. So we have large amounts of data. So hyperdimensional computing basically has to do with applications where you're computing on large vectors. So hyperdimensional means many dimensions, so like 10,000. So basically, you have this vectors that are very large, and and you use them. It's usually for AI and machine learning, you use them usually to encode some kind of models. So this application in particular is gesture recognition. So the idea is that you have to go through a large amounts of data, but the result that you get back is quite small. So you need to recognize this gesture. So you need to report back to the CPU, one number, which is the gesture ID or something. But in order to do this, you have to go through large amounts of data. So what we have here is that the data is sitting inside that PIM-capable memory. So it's just sitting there. We're not transferring it back and forth. And so the workload is embarrassingly parallel. And those GPUs are just going through this memory at very high bandwidth and are returning back only one small result. So why do I keep talking about we don't want to copy the data back and forth between CPU and this PIM-capable memory? Well, because when we do that, we're limited by those memory channels that I showed you earlier that can be quite limiting. So what we really want is we want to be using the internal bandwidth that those PIM chips have, but not external bandwidth. And a workload like this is really, really good because we have large models, and they are and we're processing them inside the DRAM chip and are not transferring lots of data outside. So you can get high memory bandwidth using other means. So GPUs have high memory bandwidth. There is HBM. And on high-end CPUs, you can add more memory channels and get higher bandwidth. But those methods are usually quite expensive. So with PIM, you can deliver high bandwidth at a lower cost in terms of dollars and watts if you're able to leverage this technology well, such as in the example that I just gave you. So, so this is just a summary of how to make the most out of PIM, and we already talked about this. But let's get back to our main thesis of the talk. So how did we get there? We said that blending of memory, processing, storage can help disaggregation. So let's see how processing in memory, where we blend memory and processing technology, can help disaggregated memory. So what if in a disaggregated memory system we had PIM-enabled memory blades? What could we do? So there are simple things that we could think about immediately, such as memory management. So each DPU can have its own memory allocator and keep a local page tables. It can even compress memory on the fly. So these are some simple things that we have implemented in our group. I want to talk about something more interesting. So remember I told you that the key problem with disaggregated memory is that the latency is several orders of magnitude higher than the latency of accessing local memory. And the problem why this latency is so important is that CPUs usually use load and store interface to access memory. So we access memory almost on every load and store instruction unless the data and instructions are cached. And even if they're cached, if we have effective CPU caching, still, if we pay in tens of microseconds to access, to service a cache miss, that will slow us down quite a lot. So the idea is that instead of using this low-level interface, we're going to let memory run either entire applications or significant portions of the application. And then, because we're not accessing memory all that often, we can use disaggregation a lot more aggressively. So one application that we think might be a killer app for this is deep learning recommendation models in PIM. So we know that ML and various AI applications love using GPUs, but GPUs are expensive. They use lots of power, and there really is difficult to find a better alternative for GPUs when it comes to training. So ideally, we want to let GPUs do what they're good at, which is training those models. And training can take days, even on really good GPUs. So if we want to run inference, we want to run something at scale. It's using a lot of data center cycles. It's something like 50% of cycles, or in that ballpark that was reported by Meta. So they use basically CPU servers to run DLRM. So one reason is cost. The other reason is that those models can be quite large and DPUs have limited memory. So inference in DLRM, parts of it, not everything, but parts of it, is very bandwidth intensive. So it's exactly the sort of situation that I described a few slides ago, where we have those really large matrices, and we have to go through a large part of this matrix, traverse it, do some simple computation on it, and return back like just a small result. And this is exactly where PIM can shine. So one idea is to take this workload and other similar ones and to implement it such that those matrices are sitting inside PIM-capable memory, and whenever we need to perform an inference, the DRAM processing units, DPUs, are traversing those large matrices at a high rate, enjoying the high bandwidth, and then they're returning to the CPU only the result. And in that case, we can have our disaggregated system where the models are sitting in a large array on the network, and then the CPU nodes are accessing them as needed for inference, and they don't use the load and store instructions, but they use a higher level API, and they move very little data back and forth. So basically, in-memory DLRM inference. So another idea that seemed like a low-hanging fruit to us is a key value store. So think about memcached in PIM. So the setup that we have in mind is, which is quite common as described in literature, application servers that access database servers. But to keep those accesses fast, there is some sort of caching, in-memory caching that sits in between, usually implemented using memcached. And we thought, well, wouldn't it be a good idea to run those memcached servers in memory using PIM? So the idea is that cache servers use general purpose CPUs. We're going to get rid of some of those CPUs, and instead we're going to put memory that performs computing, and maybe this can save us money and power. And so I can tell you already that we have prototyped this on our systems, and building purely memcached inside PIM turned out to be a bad idea, because you're moving back and forth lots of memory. I mean, if you're doing a get, you're sending the key, you're getting back the value. So all of this memory that's sitting inside PIM, you're moving it across the network. And so you're subject to those bottlenecks, local memory bus on a PIM server, and local and the network. And so what we think will be a better idea here is to implement higher level functionality, such as filtering. For example, if you have column store type of data and you're doing data analytics where you have to go through lots of data and return back a really small result, such as the result of a filter that filters out a lot of data, or your or some kind of other summary of data where the amount of data traversed during the query is large, but the result that you send back is small. So we think this is where we will get more bang out of PIM-capable memory. So to summarize, we talked about two trends, disaggregation and blending. And I told you about crazy new technology from UpMem and about some ideas how blending and processing in memory could help make disaggregation, in particular disaggregated memory, more practical. And that concludes my talk, and I'm happy to take any questions if you guys are still awake.